Radioactivity, nucleus and structure of the atom. Electron symbol E, charge minus 1.6 into 10 to the power minus 19 coulomb, mass 9.1 into 10 to the power minus 31 kg. Proton symbol P, charge plus 1.6 into 10 to the power minus 19 coulomb, mass 1.67 into 10 to the power minus 31 kg. Neutron symbol N, charge 0, mass 1.67 into 10 to the power minus 27 kg. An atom consists of three main subatomic particles, namely electron, protons, and neutrons. The nucleus is at the center of the atom. The protons and neutrons reside inside the nucleus and are known as nucleons. The electrons revolve around the nucleus in specific orbits. The total number of nucleons, protons plus neutrons in the nucleus is called the mass number and is denoted by A. The atomic number of an atom is equal to the number of protons in its nucleus and is denoted by Z. Number of neutrons is equals to A minus Z. Isotopes, isobars, and isotones. Isotopes, the atom of the same element having same atomic number Z but different mass number A is known as isotopes. Example, protium, deuterium, and tritium are the isotopes of hydrogen. Isobars, the atoms of different elements which have the same mass number A but different atomic number Z is called isobars. Example, argon, potassium, and calcium. Isotones, the atoms having different number of protons but same number of neutrons, that is, different Z and A but same A minus Z are called isotones. They have different number of electrons. Example, boron and carbon. Radioactivity, the substance which disintegrate or decay by the spontaneous emission of radiations are called radioactive substances. Example, uranium, radium, polonium, thorium, actinium, etc. Radioactive is a nuclear phenomenon. It is the process of spontaneous emission of alpha or beta and gamma radiations from the nucleus of atoms during the decay. Radioactivity emission of alpha, beta, and gamma radiation. Deflection of radioactive radiations in a magnetic field. We can observe that gamma has no deflection, alpha deflects in left direction and beta deflects in right direction. Deflection of radioactive radiations in an electric field. We can see that gamma has no deflection while alpha deflects on the negative side and beta to the positive side. Properties of alpha particle. Nature, stream of positively charged particles, that is helium nucleus. Speed nearly m. Rest mass 4 times the mass of protons, that is 6.68 x kg. Charge, positive charge 2 times that of a proton, that is equals to plus 3.2 into coulomb or plus 2e. Specific charge Q upon m is 4.79. Effect of electric and magnetic field, less deflected but opposite to that of beta particle. Ionizing power maximum 10,000 times of gamma. Penetrating power range in air small 3 to 8 cm in air. Stopping substance thin paper, human flesh. Biological damage, less damage. Properties of beta particles. Nature, stream of negatively charged particles, that is energetic electrons. Speed, about 90% of the speed of the light or 2.7 m. Rest mass, equal to the mass of an electron, that is 9.1 kg. Charge, negative charge, that is 1.6 minus coulomb. Specific charge Q by m, that is 1.76. Effect of electric and magnetic fields. More deflected than alpha particles, but in a direction opposite to those of alpha particles. Ionizing power less than alpha particles, 100 times of gamma. Penetrating power range in air, large up to few meters in air. Stopping substances, about 1 mm thick lead and about 5 mm thick aluminium. Biological damage, more damage. Properties of gamma radiation. Nature, highly energetic electromagnetic radiation. Speed, 3 m in vacuum. Rest mass is 0. Charge, no specific charge. Effect of electric and magnetic fields, unaffected. Ionizing power, minimum. Penetrating power range in air, very large, up to few hundred meters in air. Stopping substance, about 30 centimeter thick lead sheet or few meter thick concrete. Biological damage, immense damage. Changes within nucleus in alpha, beta, and gamma emission. Alpha emission, parent nucleus, X with the atomic number A and mass number Z. Daughter nucleus Y with atomic number A-4 and mass number Z-2 plus helium-42 as alpha particle. Beta emission, parent nucleus P with atomic number A and mass number Z gives daughter nucleus Q with atomic number A and mass number Z plus 1 plus a beta particle. Gamma emission, parent nucleus X with atomic number A and mass number Z gives daughter nucleus X with atomic number A and mass number Z plus gamma particle. Uses of radioactivity, radioisotopes. The isotopes of some elements with atomic number Z less than 82 are found to be radioactive. They are called radioisotopes. The radioisotopes are also prepared artificially by nuclear transmutation as they find their vital use in medical, scientific, and industrial fields. For example, cobalt, Z27A60, carbon, C, Z6A14, potassium, K, Z19A40, phosphorus, P, Z15A32, etc. are radioisotopes. Medical use. The salts of weak radioactive isotopes such as radiosodium chloride, radioiron, radioiodine are used for diagnosis. Such radioisotopes are called the tracers. These tracers are used to detect suspected brain tumors and blood clot before they become dangerous. Gamma rays emitted by the radioisotopes are used to sterilize bandages, dressings, syringes, and other equipment to make them free of germs. Scientific use. The radioactive tracers are used in agriculture science to study the effect of chemical manure on growth of plants. Example, to know how readily a plant takes in phosphate and to which part of the plant the phosphate goes. The tracers help in determining age of excavated material of archaeological importance. The age of rocks and buried plants is estimated by the study of rate of decay of carbon-14. This process is called carbon dating. Industrial use. Radioisotopes such as uranium are used as fuel for atomic energy reactors. The ionizing effects of radiations from the radioisotopes is used in making certain luminescent signs. Radioisotopes are used by engineers in factories to avoid the accumulation of charge on the moving parts of machine due to friction. Source of harmful radiation. The main source of harmful radiations are radioactive fallout from the nuclear power plants. If somehow there is an accident in the reactor of the power plant, a large amount of radioactive material and radiations will escape out in the atmosphere. 3 such accidents have already occurred. First in USA, the 3 Mile Island on 28 March 1979. Second in Ukraine, Chernobyl on 26 April 1986. Third in Japan, Fukushima on 11th March 2011. These accidents caused damage to reactor buildings and injuries to the persons working in the plants as well as to the persons in their vicinity. Nuclear waste. The fuel rods used in the nuclear power reactors are rejected when their activity decreases below a certain level. Then they are classified as nuclear waste. These rods are still quite radioactive and a source of harmful radiations. They can contaminate water and soil and affect humans and other living organisms. Other sources such as cosmic radiation and X-ray. The cosmic radiation enters the Earth's atmosphere from the Sun and from outer surface. They contain a large number of high-energy particles, of which a large number of charged particles are deviated by Earth's magnetic field, but still a substantial amount of uncharged radiation such as gamma rays and X-rays etc. reach the Earth's atmosphere. Some of these radiations are quite harmful for human beings. Apart from this, the high-energy particle accelerates also produce the harmful X-rays. Harmful effect of radiation. Harmful biological effects of nuclear radiations are of three types. Short-term, recoverable effects like diarrhea, sore throat, loss of hair, nausea, etc. Long-term, irrecoverable like leukemia and cancer. Genetic effects. Safety precautions while using nuclear energy. In a nuclear power plant, a radioactive source such as uranium-235 or plutonium-239 is used and the controlled chain fission reaction is carried out. In this process, the following aspects require special care. First, safety measures while establishing a nuclear power plant. People working in nuclear plants must be protected from exposure to nuclear radiations. In case of any accident, spread of radiations should be minimized. The nuclear reactor of the power plant must be shielded with lead and steel walls so as to stop radiations from escaping out to the environment during its normal operation. The nuclear reactor must be housed in an airtight building of strong concrete structure which can withstand earthquake, fires and explosions. There must be a backup of cooling system of the reactor core so that in case of failure of one system, the other cooling system can take its place and the core is saved from overheating and melting. Safety measures while handling radioactive materials. Operators wear special lead-lined aprons and lead gloves. They handle the radioactive material with long lead tongs. The radioactive substances are kept in thick lead container with a very narrow opening. Safety measures in safe disposal of waste. The radioactive material after its use is known as nuclear waste. The nuclear waste obtained from laboratories, hospitals, scientific establishments or power plants must be first kept in thick casks. They must be buried in the special constructed deep underground stores. These stores must be made quite far from the populated areas. The casks can also be buried in useless mines and these mines must be sealed after storing the casks. Background radiations. The background radiations are the radioactive radiations such as alpha, beta or gamma to which we are all exposed even in the absence of an actual radioactive sources. There are two types of sources of background radiations. Internal source, the radioactive substances such as potassium, K40, carbon C14 and radium present inside our body. The external source, cosmic rays, naturally occurring radioactive elements such as radon-222 and solar radiation. Distinction between radioactive decay and nuclear fission. Radioactive decay, it is a spontaneous process. The nucleus emits either the alpha or beta particle with the emission of energy in form of gamma rays which is not very large. The rate of radioactive decay cannot be controlled. Nuclear fission, it does not occur by itself. It is initiated with neutrons are bombarded on heavy nucleus. On bombardment of a heavy nucleus with neutrons, a tremendous amount of energy is released and the nucleus split into two nearly equal fragments. The rate of nuclear fission cannot be controlled. Distinction between nuclear fission and nuclear fusion. Nuclear fission. In fission, when neutrons are bombarded on a heavy nucleus, it splits into two early equal light fragments. This reaction is possible at ordinary temperature and ordinary pressure. In one fission reaction, nearly 190 mega electron volt energy is released. For the same mass, the energy released in the fission process is less than that in the fusion process. The fissionable substance is radioactive, so it gives out harmful radiations and it creates problem in disposal of waste. Limited amount of fissionable substances is available in nature. Fission process can be controlled. Nuclear reactor is based on the controlled fission reaction. Nuclear bomb is based on the uncontrolled fission reaction. Nuclear fusion. In fusion at very high temperature and high pressure, two light nuclei combine to form a heavy nucleus. The reaction is possible only at very high temperature and a very high pressure. In one fusion reaction, nearly 24.7 mega electron volt energy is released. For the same mass, the energy released in the fusion process is much more than that in fission process. The fusionable substance is not radioactive, so it does not give out any harmful radiations, and disposal of its waste is also not difficult. The fusionable substances is found in abundance. Fusion reaction cannot be controlled. This is why fusion reactor could not be constructed so far. Hydrogen bomb is based on uncontrolled fusion reaction.